Hello class. So in this video, we'll continue on section 5.2. In the previous video, we just saw some examples of calculating net area or calculating definite integrals, right? It's the same thing. When the area or the region we're trying to calculate the net area of has a really nice geometric shape. So we can use geometry formulas to calculate those areas. As I mentioned, however, that's usually not going to be the case, right? So we're going to have to find a new way to do this. Before we do that, let me give you a list of properties of definite integrals. Some we already saw, some are going to be new. They're mostly easy to remember. There's just one that's a little bit weird. Other than that, they're all pretty straight. Well, two of them, so they're a little bit weird, but makes sense. Okay. Other than that, it's pretty straightforward. So these are the properties. Suppose f and g are both integrable. Let's just remember for us, what's the property of being integrable? Well, as long as the function is continuous, the function is integrable. Right? The definite integral exists. So this function being integrable, it's the same thing, interchange it with the function being continuous. This means that the derivative exists. The integral exists. So the integral on whatever interval it is exists. Right? Same for g. Right? Suppose f and g are integrable on AB. P is any number in AB. Right, so any x value in that interval, and c is any constant. Then we have a few properties. First of all, the integral of b to a of f of x dx equals the negative of the integral of a to b of f of x dx. Now, what does that mean? This is one of the two that I say that are not kind of intuitive, but the idea is, for example, you have the integral of 1 to 2 of, let's say, 2x dx. Well, by this property, that means you can change the order of integration here. So change the bounds. It's the same as calculating the area or the net area going from 2 to 1. So just change the signs. Now, for us right now, this doesn't mean much of anything. But when we start to compute these integrals, definite integrals using antiderivatives, this might simplify our work in some cases. Right? For now, it doesn't really make much sense. I would really never use this property because again, for us right now, it doesn't really do much. One that makes a little bit of sense is that the integral of a to a of f of x dx is 0. What does that make sense? Think of what that looks like. You're trying to approximate the area using rectangles. Well, the interval is just itself. It's just a point. What's the length of a point? That's 0. Okay, so multiply the length of a point, which is 0, times the height. Well, it doesn't matter what the function value is, as long as it's finite. 0 times a finite number is always 0. Okay, so that's the idea for this. If you're integrating over an interval, which is just a point, the integral is always 0. Or another way to think of it, the net area is 0. Right? So think of that one that way. Okay. Now this one we've seen. We can separate the integral. We saw it for antiderivatives. It works the same for definite integrals. Right? So we saw it for indefinite integrals, works for definite integrals. If you have the integral of a to b of f of x plus g of x, you can separate the sum. Right? So you can separate it as the integral of from a to b of f dx plus the integral of a to b of g dx. Right? So that's 3. 4, we also saw for indefinite integrals. It works the same here. You're trying to find the definite integral of a to b of a constant times f dx. You can move the constant outside. Just calculate the definite integral from a to b of f dx, and then multiply the constant back in. So we've seen both of these before. This one also makes a little bit of sense. Right? So remember, p is some number between a and b. So what this is saying is if you want to find the net area bounded by f and the x-axis from a to b, you can partition it as first doing it from a to p, and then doing it from p to b. So let me give you an example of this. Suppose we have some function here that looks like this. Let's say this is b, this is a, and there's some p here. We want to find the net area, or the integral from a to b of f dx. We're looking for this area. Okay. What is this saying? Well, you can break finding the area into pieces, which we already did in the example in the previous video, right? So you can first separate it like this, calculate the area from the net area on the interval a to p, and then add the net area on the interval from p to b. That's the same thing as saying that the integral from a to b of f dx equals, well, we just find the area first from A to P, and then add the area or net area from P to B. So in a picture, it makes sense, right? You can always partition your interval into smaller intervals and just calculate the area in each smaller interval. So that one makes sense. The last one, which is a little bit hard to explain, kind of like the first one, is this one. So we know that a definite integral calculates net area. What if we want to use a definite integral to calculate not net area, but area? Meaning that if the region is below the x-axis, we just still want to count it as positive. We just want to find the area independent of whether it's above or below the x-axis. How do you do that? Well, you do it by integrating not the function f, but the function absolute value of f. Why? Because what does absolute value of f do? It makes the function positive. So, for example, we have a function that looks something like this. So like this on this interval, and like this on this interval. Right? So this is, suppose this is A, this is P, and this is B. Right? We want to find the net area. Well, we're looking at this here. Right? And assuming this is F. Well, what does the graph of absolute value of F look like? Well, just whatever is below the x-axis, you move it up, above. So you reflect it about the x-axis. So absolute value of f looks like this. And everything else stays the same. This is still A, this is still P, this is still B. And now you're just calculating area with everything positive. So that's why that works. You want to find use definite integral notation to find not net area, but area. Just integrate, instead of the function, integrate the absolute value of the function. And again, what that does is it makes all of the function be above the x-axis while preserving the area, right? So notice that the area of this region here is the same as the area of this region here. But when it's below the x-axis, we count it as negative. So how do we get rid of that? We make everything below the x-axis move above the x-axis. We do that by taking the absolute value of the function. So in the picture, it kind of makes sense. So just try to remember this picture. If you're trying to figure out what is happening here, when you integrate the absolute value of a function, right? You're just calculating area instead of net area. Okay. So those are the 6 main properties that we're going to be looking at with respect to integrals. I don't know if these are formulas that are going to be given to you in exams, for example, in the final, but again, most of them kind of make sense. Right? Again, 3 and 4 we already knew, right? We can separate integrals, we can move constants out. 2 kind of makes sense. If you're integrating over a point, well, what's the area of a point? No matter what the height is, that should be 0. Number 5, again, also makes sense. It just means you can calculate the net area by partitioning the interval, like we showed here. And then 1 is one that you kind of, okay, you just have to memorize. I can change the bounds. I just have to put a negative in front. So I can go from 1 to 2. Instead of that, go from 2 to 1. I just add a negative in front. For this last one, again, just think of it as calculating area compared to calculating net area. Integrate f, you're calculating net area. Integrate absolute value of f, you're calculating area.